To determine the length of a curve such as the St. Louis Arch, integration once again comes to the rescue. Many people think that the St. Louis Arch is an upside-down parabola, but actually it is a very unique and unusual function called the hyperbolic cosine. The name hyperbolic function came from the comparison of the area of a semicircle with the area under a hyperbola. The trig portion of the name hyperbolic cosine came from the calculus features that the hyperbolic function share with the trig functions. For example, the derivative of the cosine of x is negative sine of x, whereas the derivative of the hyperbolic cosine of x is the hyperbolic sine of x. To understand how the formula for arc length was discovered, consider the following graphs. If we wish to estimate the length of the top curve, we could measure the lengths L1, L2, and L3, and they would be very close in size to the arc lengths S1, S2, and S3. If we would like to get a more accurate measurement, we could form more and more line segments connecting the points on the curve that are very close to one another as they are in figure 2 down below. If we let the points get infinitely close to one another, delta S is approaching 0, and we arrive at the integration process. Consequently, the arc length formula is derived directly from the algebraic equation for the distance between 2 points. S is equal to the square root of, in parentheses, x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Or a familiar form that we often use in calculus is delta S is the square root of delta x squared plus delta y squared. If we were to divide delta x squared and delta y squared by delta x squared, we would then have a 1 plus delta y over delta x squared inside that square root. As delta x approaches 0, delta y over delta x becomes the derivative dy dx. Finally, we arrive at the calculus formula for arc length. S is equal to the integral from a to b of the square root of 1 plus the derivative squared. Using the information from the St. Louis Arch, we now have S is equal to the integral from negative 299.2239 all the way up to 299.2239 of the square root of 1 plus the hyperbolic sine of 0.0100333x that needs to be squared. This integral is best found by using your calculator. The hyperbolic sine is located in the catalog of the TI-83 or 84. Catenary curves are created naturally by hanging wires. In this example, we're going to find the length of a catenary. What we have is electrical wires being suspended between 2 towers. They form a catenary modeled by the equation y is equal to 2 hyperbolic cosines of x. Negative 20 less than or equal to x less than or equal to 20, where x and y are measured in meters. The towers are 40 meters apart. Find the length of the suspended cable. First of all, we find the derivative of y is equal to 2 hyperbolic cosines of x, which happens to be 2 hyperbolic sines of x. We substitute in the formula that were given before, and we get the following integral. S is equal to an integral from negative 10 to 10 of the square root of 1 plus 2 hyperbolic sines of x being squared. We integrate if possible, otherwise estimate the solution using your calculator. This problem again needs to be put in your calculator, so why don't you give it a try and see what you get. In summary, finding the arc length of a curve is a matter of plugging the function's derivative and its limits of integration into a formula derived from the distance formula. Often, the hardest part of the problem is typing into your calculator. Gotta watch those parentheses.